All right, number one. How many grams of calcium chloride are needed to prepare 5.17 liters of 0.5 molar calcium chloride solution? So this goes back to the definition of molarity. Let's see, let me pin my video. Let's see better. Yeah, cool. Just a little bit more. There we go. Okay, so what are we given? Well, first of all, we've got calcium chloride to deal with. We're going to make a solution out of it. And the final concentration of calcium chloride is 0.5 molar. Okay? And our final volume is 5.17 liters. Okay, so we'll go back to the definition of molarity. It is moles per unit volume, which in this case is liters. So we have that already right here. What we don't have is moles. And the question is not moles, but grams. It wants to know the mass of calcium chloride. So we have molarity also, 0.500. And moles is our unknown in this calculation. So you have to ask yourself, if I solve this for moles, can I go from moles to grams? And the answer obviously is yes, because we know the molar mass of calcium chloride. So once we determine the moles, which will be molarity times volume. Okay, so let's see, can I do that in my head? 5, 6, 7, 8, 5 moles. I think that's right. Maybe I better use my calculator just to be safe. Oh, I got that one right. Okay, so we know moles. Now we need to convert moles cancel moles, leave us with grams. And the magic number there is 111 grams per mole. And that's 28, let's see, 3 significant figures. 287 grams. Okay, so there's your answer. All right. That's number one. Now we'll look at number two. What mass of solute is contained in 64.9 milliliters of 2 molar sodium bromide solution? So we're given sodium bromide. There's your formula. We're given the volume equals 64.9 milliliters. And we're also given the molarity is equal to 2.0 molar. Okay, and then the question is, what mass of solute? What's the mass of this? All right, so we'll go back to our formula. Molarity equals moles per unit volume. We need to know moles in order to determine mass. So solving for moles, we get mass times volume. The volume has to be in liters. So we got to convert this to liters. So That in liters is 3 positions to the left, 1, 2, 3. So that's 0.0649 liters. Now we have the information we need to get to moles. Then we have to go to mass. So moles is equal to that, and then 0.0649 liters. I could probably do this one in my head, but I don't want to strain myself this early in the morning. Let's see, that's 12.98. I'm going to keep an extra significant figure there just to avoid rounding errors, and that's wrong. 0.1298 moles. Okay, so now we need to convert moles to mass. And we need a conversion factor that looks an awful lot like molar mass. So what's the molar mass of sodium bromide? Well, it's not given to us. So we have to calculate it based upon the periodic table. The molar masses of sodium and bromine. And that means you've got to be able to write this correctly. Sodium is +1, bromine is -1, so that's it. Sodium and bromine, just one of each. Sodium is 23. And bromine is 79.90. 102 grams per mole. So 102.9. There we go. So we just multiply that value times 102.9. And we get 13.4 grams. There's your answer. Okay. All right, number 3. In this case, now that's a lot of wording right there. So we're going to have to break this apart. We're going to have to extract the information and put it on the board in a form that looks more familiar. But let's see. What are we looking at? Calculate the concentration of silver ions in solution C. Okay, so what are we doing? 3 liters of 3.67 molar sodium chloride, that's solution A, and 2 liters of 2 molar solution silver nitrate, solution B. You mix those together to make solution C. What's the concentration of silver ions in solution? Okay. This takes several steps. First of all, you're going to combine 2 solutions of these compounds, sodium chloride and silver nitrate. So we need a balanced equation to express that reaction. Sodium chloride in solution and silver nitrate in solution are going to react. And what are they doing in solution? Well, first of all, is this correct? 1 sodium, 1 chlorine. Yeah, that's right. 1 silver, 1 nitrate. That's correct. In solution, you've got individual ions, sodium ions, chloride ions, silver ions, nitrate ions. Now they have a chance to interact once we put the solutions together. So what you have is silver. You're looking for any precipitation, that is, any solids that might form. If we combine sodium and nitrate, you look at your chart, solubility chart, and that says that sodium nitrate is soluble. Okay? And you look at silver and chlorine, and you find out that that forms a solid. Okay? So are we balanced? In fact, as a matter of fact, we are balanced, just like that. Now let's put the information up here that we know. 3 liters of 3.67 molar solution of sodium chloride before we put them together. Silver nitrate, we have 2 liters of 2 molar. Okay? This solution A, that's solution B. Solution C is all of this. Well, actually this. But remember, if we have absolute amounts of these 2 reactants, one of them is going to run out first. One of them will be limiting. And that limiting character will stop the reaction when it's used up. So how do you tell which one's limiting? You have to convert to moles. You've got to know moles first. So how do we get moles out of this? Well, molarity times volume is moles. So all we have to do is multiply these together, like that and like that. So this one's easy. That's 4 moles of silver nitrate. How about this one? Let's see if I can do that one. 2 and 18 is 20, and 2 and 9 is 11. Let's see if I did that right. Yep. Okay. So this is moles of sodium chloride. Notice also that since these are ions in solution, 11.01 moles of that compound is also 11.01 moles of sodium and 11.01 moles of chloride ions, or 4 moles of silver ions and 4 moles of nitrate ions. Okay, now which one runs out first? Well, we could do a calculation and we could say, okay, how much silver chloride would this make? And how much silver chloride would that make? But this is an easy reaction to quantify because all of the coefficients are 1. If you have one of these, you'll have one of those. Unless this one runs out first. But look, this one's 4 moles and that one's 11 moles. Which one's going to run out first? That one. Fewer moles. Makes less silver chloride. Okay, so this one is limiting. It will run out first. And if we go back and look at the question, what's the concentration of silver ions in solution? If this one runs out first, those silver ions are going to be all consumed. Every one of them. Okay? So the answer to the question is simple. There's no silver ion left in solution. It's 0 molar. Okay? That's why the answer is C. So 3 looks like a really hairy problem. And I could have made it that way. But I just wanted you to be able to write the equation, put the information in, find out which one's limiting, and see from that determination that there's no silver left. So the answer is 0 molar. There is no silver left in solution. It's all consumed. All right, that was 3. Let me scroll a little bit and get the rest of it. Here we go. 4, 5, and 6. the molarity of chloride in 110 milliliters of a solution containing 3.22 grams of calcium chloride is what? Okay, so in order to determine the chloride concentration, calcium chloride will go into solution. You can look it up in your chart. Calcium across the top, chloride's down the side, follow them to the middle, it's completely soluble. So calcium chloride is going to put all of those chloride ions in solution. What we have to do is find out what is the concentration of this compound and then relate that to the amount of chloride ions. And so we're given 3.22 grams of calcium chloride. And we're also in 110 milliliters of volume. Let's see, let's put volume here. 110 milliliters. Okay, so how do we find the concentration? We need moles. We've got to convert this to moles. In fact, the molar mass was given in a previous problem, and it was 111 grams per mole. So that'll give us the moles of that formula unit. Why don't we go ahead and do the chloride while we're here? Just change our conversion factors together. This is moles of calcium chloride. We want chloride ions. So calcium chloride and chloride ions, what's the ratio? Well, for every one calcium chloride, there are 2 chloride ions. So you get 2 for 1. That cancels this one. Now we can express the number of moles of chloride ions. Just crunch a few numbers. 3.22 divided by 111 times 2. And I get 5.80 times 10 to the minus 2. Ten to the minus 2 moles of chloride ions. Now we can do our calculation. Moles per liter, 0.110 liters. I just moved the decimal 3 to the left. So the molarity is 5.80 times 10 to the minus 2 moles of chloride divided by 0.110 liters. Now let's see, was that the question? Yes, the molarity of. Okay, so let's divide 0.11 into that number. And I get 0.527, 3 significant figures. 0.527 molar. Number 4. Oh, here we go. Now, the closest one to it is 528. Let me see. I know what happened. This is the rounded number for that calculation, and I left all the decimals in there. So your best answer is 0.528. Let's see if I'm right here. Let's see. 5.8. Let's go 2 minus 0.11. Actually, 527 is a better answer. But we don't have 0.527 up there, so we pick the best one, and that's 0.528. All right, that's number 4. Number 5. What volume of 12 molar nitric acid is required to prepare 6.71 liters of 0.1 molar nitric acid? Here we have a concentrated solution and a dilute solution. This is a dilution problem. Remember the formula that applies there. The molarity of the concentrated times the volume of the concentrated solution that you draw out of that is equal to the molarity of the diluted solution times the volume, the final volume of the diluted solution. So what values do we have? 12 molar nitrogen. 12 molar. That's the concentrated. What volume? We don't know yet. That's our unknown. The final molarity is 0.1 molar. And the diluted volume is 6.71 liters. Now, notice the answer is in liters here. So we should leave that value in liters so that our answer will come out as liters. If these were milliliters, if we had milliliters as our answers, we convert the diluted volume to milliliters and then our answer would come out as milliliters. But as it is, 6.71 liters gives us our formula, and we just solve for this one. Okay? In the interest of time, I'm going to take the key at its face value, 0.559 liters will be the solution to that problem. All right, number 6. You've got 3 liters of 3.48 molar sodium chloride solution, 2 liters of 2 molar silver nitrate. This looks familiar. Mix them together. Calculate the concentration of sodium ions in solution. Okay. We put the equation up here before. All you have to recognize is that sodium chloride plus silver nitrate yields sodium nitrate plus silver chloride. That's the solid. These are all aqueous, aqueous, aqueous. Okay, notice that the complete ionic equation, of course, would have sodium ions, chloride ions, silver ions, and nitrate ions. And this would have sodium ions and nitrate ions, and that's a solid. That would be the complete ionic equation if we spread those out. Well, the point here is that what's the net ionic equation? The net ionic equation will keep this one and this one to make that one, and that one, that one, that one, and that one will be cut out because they're spectators. Spectator ion means that there's no reaction involving the spectators. Sodium stays sodium in solution, right? So if you start off with 3 liters of 3.48 molar, then how many moles of sodium chloride do you have? Right, so that's 4, 2, 12, 14, 11.44 moles of sodium chloride, which means you got that many moles of sodium as well. Okay. So that's how many moles of sodium you start with. How many moles do you end with? You still got that many moles of sodium in solution at the end. So what's the concentration? Well, it's not 3.48 molar again because you diluted it with that solution. So how many liters of this solution are there? The second solution, 2 liters. Okay, so you have a final volume of 5 liters. So this many moles per 5 liters will give you the concentration of sodium in solution. And I get 2.29 molar sodium ions. Let's see, did I do my calculations correctly? Maybe not. Let me check my math now. 3, enter 3.48 times. It's 10. See, that's what I get for doing it in my head. 10.44 and divided by 5 is 2.09. There we go. And there's your answer. The point of this exercise is to recognize that sodium is a spectator. Its concentration changed because we diluted it. But we didn't use any sodium in the reaction. Okay, that was 6. Let's see, let's skip down to, let me check how much more time we have actually. 8:30. Okay, we got a little over an hour. I'm going to skip down to 9. Come on. All right, it's not behaving. There we go. You have 3 ammonium sulfate solutions on the table in front of you. All of the solutions are derived from 500 milliliter volumetric flask containing 3 molar ammonium sulfate. Solution 1 is 127.2 milliliters. They're all the same concentration. Solution 2 is 68.7 milliliters, and solution 3 is 32.4 milliliters. All right, how many moles of ions does solution 2 contain? All right, so there's a lot of blue smoke in this one, right? You don't care about 1 and you don't care about 3 because the question is about 2. So we look at solution 2. Solution 2 is 68.7 milliliters of 3 molar ammonium sulfate. Ammonium there has 1 plus charge. Sulfate has a 2- charge. So we have to balance the charges. This is an ionic compound. So we need 2 of these positives. And since ammonium is a polyatomic ion, we can't change the subscripts. We need a parenthesis. So that's the correct way to write ammonium sulfate. And if you don't write it that way, then you can't answer the question. The question is, how many moles of ions are contained? Right? So we've got molarity times volume is moles. So we have 3 molar times milliliters. No, liters. We need liters. 0.0687 liters will give us moles. So I'm not going to do that one in my head. I run into trouble when I do that. Okay, 20.61. 20.61 moles. Does that look reasonable? No, it doesn't. I went the wrong direction. 0.2061. 2061. Yeah, I checked myself midstream to be sure, right? That fractional number times this, it can't make it bigger. I just read it wrong. So that's how many moles of compound. All right. How many moles of ions do you have? Well, we need to convert. Cancel compound and give us ions. So what's the relationship here? For every mole of compound, you have 1, 2, 3 moles of ions. These polyatomics do not break up in solution. They're intact. So you have 2 ammoniums and 1 sulfate. So it's 3 ions for every 1 compound. So we need to multiply that value times 3, which is 0.618, 0.6183, and we can keep 3 significant figures, 0.618 moles. And here we go, 618. All right. Let's see, go from 9 to actually 10, and 10 is good. A mixture of sand and water is what? It's not a solution. It's not a homogeneous mixture. It's a heterogeneous mixture, right? And that's not one of our selections. So it's none of these. Okay. Solvent and solute are only valid for solutions, homogeneous mixtures. So solution, solute, solvent, they all go together. Aqueous solution, well, it's a special kind of solution, but this is not a solution. So the only answer that can be is E, none of these. About 11. I need to scroll that one. Here we go. Number 11. A chemist needs 225 milliliters of 3.1 molar hydrochloric acid. What volume of 12 molar must be dissolved in water to form this solution? Okay. This is same as before. This is a dilution problem. What are we given? Well, we need to fill in these spaces. Concentrated molarity times concentrated volume equals diluted molarity times diluted volume. So what values do we have? We need 225 milliliters of this diluted solution. 225 milliliters. Right? And the question is, what volume of the concentrated? Right? All our answers are in milliliters. So we're going to leave that volume as milliliters so that the answer will come out as milliliters. Molarity of the diluted, we need 3.1 molar. 3.1 molar. Okay. The question is, what volume of the concentrated do we need? Okay. And we're working from 12 molar. Okay. Now all we have to do is solve for the volume of the concentrated solution that needs to be diluted to that volume. And to save time, we need 58 milliliters. Is that reasonable? Well, 12 times 58, say 10, it's 120 or 30. Right? No, 1,200. No, wait a minute, that's not right. I better do this calculation to be sure. 3.1 times 225, and then divide by 12. 58.1, or 58, because we only have 2 significant figures there. Okay, so it's right. That was number 11. Let's see. Skip to number 13. Come on. It's not working for me. There we go. I scrolled it anyway. Number 13. You've got 250 milliliters of 4 molar sugar solution, and you add 376.3 milliliters of water. What's the concentration of the sugar solution after the water's been added? Okay, we're diluting the solution. Right? So if we say the concentrated molarity times the volume of the concentrated is equal to the molarity of the diluted times the volume of the diluted. So the concentration here is 4 molar. And the volume of this solution is 250 milliliters. The question is, what's the concentration of the diluted solution? That's our unknown. The trick is, what's the final volume? Well, we added 376.3 milliliters to the former volume. So the final volume is the summation of those two, is 250 plus 376.3. That's the trick. Let's see. Okay. I thought I saw an error. Okay, we're good. Yeah. Okay, so if we solve this for that value, we add these together, we divide that into this product, we should get 1.6 molar. All right. That was 13. Let's see, 14. Let's see, this marker's giving out on me. You have 2 hydrochloric acid solutions. Label solution A and B. Solution A has a greater concentration than solution B. Which of the following statements are true? All right, so let's reason this first before we look at our choices. You have 2 solutions, A and B. Okay. So the concentration of A, excuse me. Solution A has a greater concentration than B. So the molarity of A is greater than the molarity of B. That's given. What does this mean? This means that you have so many moles of A in so many volume, such and such a volume of A, and so many moles of B in such and such a volume of B. That still is true because this equals that. Okay? Now we can say something about what would happen. Why is this one greater than that one? That's because this is bigger and that's smaller. Right? Because this is a quotient. So if that's bigger and this is smaller and that's bigger. Now let's look at our choices. Which of these statements are true? If you have equal volumes of both solutions, B contains more moles. You have equal volumes. So if you have equal volumes, that means this one has to be bigger than that one. A has to be bigger than B. B does not contain more moles. A does. So A is false. A is false. Adding more moles of HCl to both solutions will make them less concentrated. Well, that's ludicrous. If you add more solute, concentration is going up on both of them. So B is false. To obtain equal concentrations, you must add a certain amount of water to solution B. What happens to B if you add water to it? If you increase this, it makes it less concentrated. Right? So it's never going to have the same concentration as A if you keep diluting it. C is false. At least two of these above are true. Well, no, it can't be because they're all false. How about E? Well, the E is the only one left. If you have equal moles of HCl in both solutions, if this is equal, solution B must have a greater volume. That's true because of the nature of a quotient. In order for this one to be less concentrated than that one has to be bigger in volume if these two are equal. So E is true. That's the one. And I might add, you can't just sit there and stare at this question and the answer pop off the page. You've got to look at it as for what it is. What does it mean? What do these concentrations mean? Then you can answer the questions. Okay, that was 14. Let's skip down to 16. Better scroll it. All right. 16. A 116.9 gram sample of nitric acid solution, 70% nitric acid by mass, contains how many moles? Right. What's our definition? Mass percent. So 70% means 70 grams of nitric acid per 100 grams of solution. Right? Parts per 100. 70 parts per 100. That's what that means. If we have 116.9 grams of this sample, grams of that solution, then we cancel solution, and that leaves us with grams of HNO3. Right? So we just need to multiply 70 times 116.9 and then divide by 100. So that's 81.83. 81.83 grams of HNO3. But that doesn't answer the question, does it? The question is how many moles? So we got to convert this to moles. Right? Cancel grams, leave us with moles. So what's the molar mass of HNO3? Well, let's see. Hydrogen is 1.01. Nitrogen is 14. And oxygen is 16 times 3. 3 times 16 is 48. Right, so we have 1, 0. Maybe I can do this one, man. 13, 1, 5, 6. 6301. There we go. 6301 divided into that number is 1 point, let's see. Actually, let's see which one comes closest. I'll keep all my decimals. 1.2987 moles. Now, which one comes closest to that? 1.30 comes closest. Well, if we say none of these, it depends. if we're saying 70.0, excuse me, that was my mistake. We do have three significant figures. So 1.30 would be correct. That was number 16. Let's see, that's number 17. We'll do 17 also. Determine the normality. 17. So we're looking for the normality of a base. 93 point base if 93.0 milliliters of 1.8 molar HCl is required to neutralize 52 milliliters of it. Okay. What do we know about if we got exact neutralization? That is, the number of moles of hydrogen ions is equal to the number of moles of hydroxyls. Okay. So that reaction, for acid-base reaction, that is true no matter what. We just need to find out how many equivalents of hydrogen there are. And since hydrochloric acid is monoprotic, then the molarity is equal to the normality. So 1.8 molar equals 1.8 normal, which is equal to 1.8 equivalents per liter. And in equivalents, we're talking about hydrogen ions. Okay? So if it's 1.8 equivalents per liter, then we can use this expression. Normality of the acid times the volume of the acid equals normality of the base times volume of the base. So we know the normality of the acid, 1.8 normal. What's the volume of the acid? 93 milliliters of 1.8 molar. 93 milliliters. What's the normality of the base? We don't know. That's unknown. Okay. What's the volume of the base? 52 milliliters. Okay. This is the thinking part. Now we're just crunching numbers. So 1.8 times 93 and divided by 52 is, let's see, three significant figures. I left the zero off of that, 0.0. And 1.8, well, no, that's only two significant figures. So we've got 3.2 normal. Okay, so that's why the answer is B. All right, that was 17. Let's see. Oh, we lost somebody. Oh, that's right. She had a doctor's appointment. Okay. 18. Let's see. Can I page? Nope, wrong way. Yeah, there's 18. Okay. Magnesium metal reacts with hydrochloric acid. That's true. To form magnesium chloride and hydrogen gas. So magnesium metal reacts with hydrochloric acid, aqueous, to yield magnesium chloride in solution plus hydrogen gas. So are we going to need this one to be? Yeah, we're going to have to balance this one. So we've got two hydrogens here. We need two hydrogens there. That gives us two chlorides, one magnesium. That's it, we're balanced. Just one change and we're balanced. Okay, suppose we react in excess of magnesium metal. All right, so we got plenty of this. With 19.8 milliliters of hydrochloric acid at a concentration of 3 molar. Okay. And we collect all of the hydrogen gas in a balloon. So this gas is going to be at 25 degrees Celsius, 1 atmosphere. Okay. What's the volume of that balloon? Now let's work this problem backwards. If we're looking for the volume of a gas, and this is a state, not a before and after. This is a state, so we need the universal gas equation, or the ideal gas equation, I should say. PV equals nRT. So we know what R is, it's a constant. Temperature is given, we just have to convert that to Kelvin. Volume is our unknown, pressure is 1 atmosphere. We can solve it as long as we find out the number of moles. So we need to know the number of moles of hydrogen gas. So we work back here, we're doing stoichiometry now. So 19.8 milliliters is how many liters? 0.0198 liters, right? 1, 2, 3. So that'll give us the number of moles of hydrogen chloride, or hydrochloric acid. So let's do that one. 0.0198. So that's 5.94 times 10 to the minus 2 moles of HCl. Right? So what's the relationship between hydrogen chloride and hydrogen gas? Let's get that out of the way. We need to convert, right? HCl, H2. So the coefficient is 1 for this one, 2 for that one. We need to take half of that value, which is 2.97 times 10 to the minus 2 moles of hydrogen gas. Okay, now we know the moles. So if we say PV equals nRT, then solving for volume is nRT over P. We need to convert this one to 98 K. And what's R equal to? Let's see, volume equals moles, 2.97 times 10 to the minus 2 moles times R. I'm going to need some space here. 0.08206 liter atmospheres per mole K. Okay. And temperature is 298 K. All of this is divided by 1 atmosphere. Okay? So now we just solve that equation. I've already got that in my calculator, so 0.08206. This value for R is in the useful information. In every review document we'll have that. After we studied gases, that was there. and then 298. And divided by 1, obviously, is 7.29 times 10 to the third liters. Now, how is it listed? What did I do wrong? Okay, I did something wrong. I've got a decimal out of place here somewhere. Let's go back and figure. This should be 0.0198. That's probably where I made my mistake. So this is 0.0594, 0.0594. Okay, that's the volume. No, excuse me, that's moles. And then it'd be half the moles there. So that's 0.0297. 0.0297. That's right. That's right. That's right. And that's right. So let me put it in again. 0.08206 times 8 times 0.726 liters. There we go. Calculation error. 0.726 liters is our answer. About 3/4 of a liter out of that experiment. All right. Now we'll see. We'll skip down to 22. There it is. I need a better marker. Here we go. Which of the following solutions contains the smallest number of ions? Okay. We're going to need to set up a Henry Ford here, an assembly line. We're trying to find the smallest number of ions out of this group. So we've got A, B, C, D, and E. At least 2 of the above contain the same number, and they're the smallest. Right, so we got to do every one of them. 246. How do we find the number of ions? First, we find the number of formula units. So we need a volume times molarity. 246.8 milliliters. 539.8 milliliters. 305.6 milliliters. And 189.6. Okay. And now we need the concentration. 1 molar, 1 molar, 2 molar, and 2 molar. Okay. This will give us the number of millimoles. Right? Milliliters times molarity is millimoles. Will give us the millimoles of the compound. But we want to cancel the compound and leave us with ions. So we need the relationship of number of ions to the moles of compound. And for that, we need to know the formula of each one. Sodium sulfate. Sodium sulfate. 2 sodiums, 1 sulfate because, so the sulfate has 2 minus charge. Sodium only has 1 plus. Lithium nitrate. Lithium nitrate. They're both equal. -1 plus 1. Potassium hydroxide. -1 plus 1. Iron-free chloride. That's a -1. This is a 3 plus. That means this one is 3. So now we can count the ions. This one has 1, 2, 3. This one has 2. This one has 2. This one has 4. Okay. Now we can solve our equation. So 246.8 plus 1 times 3 is 740. Right? 1. Yep. 740 moles. All right. 539.8 times 1 times 2. This is 1,080. 305.6 times 2 times 2 is 1222. Okay, and the last one, 189.6 times 2 times 4 is 1517. So we just compare the moles of ions, right? That's the big one. Next one, that's the smallest one. So A. And E can't be the answer because none of them are the same. All right, let's see. 18, oops, I already skipped. 22. Wait a minute, I already did 18. 22, okay, now skip down to 25. Let's see, I better scroll. That was crapping out on me. Assume that vinegar is 0.852 molar solution of acetic acid. What volume of 0.2136 molar sodium hydroxide would be needed to completely neutralize 6.89 milliliters of vinegar? In this one, notice that vinegar has 1 proton per molecule. So its molarity and normality are equal. Sodium hydroxide has 1 hydroxyl per molecule. So its molarity and its normality are equal. So we can use that expression. All we need to do is say the normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. So the normality of the acid is 0.852 normal. And the volume of the vinegar is 6.89 milliliters. Okay, the normality of the base is 0.2136. All right, and the volume of the base is our unknown. And notice, if we put one volume in milliliters, the other volume has to be in milliliters also. So let's see what it is. This one times that one divided by this one. And I get 27.5 milliliters. Volume of the base, 27.5 milliliters. There it is. Okay, that was 25. Let's see, the next one I got marked as 26. For the reaction between 200 milliliters of 0.1 molar silver nitrate and 95 milliliters of 0.1 molar sodium chloride. So here's that same reaction again. Sodium chloride and silver nitrate yield sodium nitrate and silver chloride solid. The concentration of silver ions in solution after the reaction is complete is. Let's look at the answers. The silver ions do not participate in the chemical reaction. That's false. Without the silver ions, you won't have a reaction. Less than 0.1 molar would be the concentration of silver ions. All right, we're going to have to write the equation and check our limiting reactant, just like we did before. Let's try that. So we have sodium chloride plus silver nitrate. That's not going to work. Yields sodium nitrate plus silver chloride, solid. Okay, now we're given 200 milliliters of 0.1 molar silver nitrate. 200 milliliters of 0.100 molar. In 95 milliliters, another 0, of 0.1 molar, 0.1 molar sodium chloride. All right, so which one's limiting? Well, we've got equal molarity, but this has got more volume. Right. So this one's going to be limiting. Okay. If we multiply this molarity times this milliliters, we get 9.5 millimoles of sodium chloride. And we multiply this one, we get 20 millimoles of silver nitrate, which means we have 20 millimoles of silver and 9.5 millimoles of chloride. All right, so we're going to use up 9.5 millimoles of this silver amount. Let's see. 10.5, yep, millimoles of silver ions are left over. So what's the volume? 295 milliliters. Remember, millimoles divided by milliliters is molarity. So that's 10.5 divided by 295. Oops, 95. Let's try that again. So I get 0.0356. 0.0356. molarity of silver ions still in solution after we used that part of it. Now, why did I put 295 milliliters here? Because we diluted 200 plus 95, right? And this is what's left. So this is the concentration of silver in solution. Now we can answer the question. Less than 0.1 molar silver ion concentration. That's true. This is also true. Less than 0.1 molar. The rest of them are not true. But how about the rest of the statement? Some but not all of the silver ions are used to make the precipitate. That's true. Even though silver ions do not react, they are diluted when, okay, that's false. Silver ions do react. Right, so B has to be the correct answer. All right, that was 26. And I need to get a new marker. Oh, here's one. We'll see if this one works. 26, let's skip down to 29. Oop, too far. I'm gonna have to scroll. There we go. 29. A nitric acid solution containing 71% HNO3 by mass has a density of 1.42 grams per milliliter. How many moles of NHO3 are present in 2.36 liters of this solution? Okay, first of all, this means 71 grams per 100 grams of solution. 71.0 grams of HNO3 per 100 grams of solution. Remember I said early on, a lot of chemistry problems can be solved by dimensional analysis. You just keep track of your units. As long as you don't disobey any chemical laws, then you can solve the equation this way. And this is what we're doing. All right, so that's the concentration. And we have 2.36 liters of this solution, right? How many grams of that solution do we have? I don't know yet, but can we find it? We need to know how many grams of solution in order to find out how many grams of HNO3. And then we have to convert HNO3 to moles. Actually, we probably should start from 2.36 liters of the solution. Then we can get rid of liters and leave us with grams. Well, except we can't do that. We need to know milliliters. 1,000 milliliters in a liter. Okay, now we can use density. Grams per milliliter, 1.42. Okay. Cancels milliliters. Now we know how many grams of the solution that we have. So if we know that we have that many grams of solution, now we can cancel grams of solution and give us grams of HNO3. Now we can convert grams of HNO3 to moles. All we need is the molar mass. So for every, how many grams per mole? All right, we need the molar mass of HNO3. I did that before, 1.01 14, and 48. So that's 1, 0, 12, 13, 1, 4, 5, 6, 6301. There we go. So that's the hard part. The rest is crunching numbers. And we know that we're right because we're left with moles of HNO3. All right. So let's see if I did that correctly. 2.36 times 1,000 times 1.42 times 71 divided by 100 and divided by 63.01. So I get 37.8. $37.8 moles. There it is. Okay? That's dimensional analysis. '29, let's see. Let's skip down to, we're going to do a lot of skipping. Must be some repetitive. Here we go. How about 55? There it is. 55. All right, this one's nothing wrong on me. I can go to my reserves. Okay. In the following acid-base neutralization, 1.61 grams of solid C6H5O. I don't know what that is. I'm guessing that's phenol, right? There's neither here nor there. We've got the formula, and there's our acidic proton. So it's 1 proton per molecule is neutralized. This much acid neutralized 11.61 milliliters of aqueous sodium hydroxide solution based on this reaction. Okay? Calculate the molarity of the base solution. All right. So we have H. C6H5O. Looks like it's coming along. Plus sodium hydroxide yields water plus sodium C6H5O. Okay, so now what are we doing? 1.61 grams of the solid. All right. And 11.61 milliliters of this solution. All right. What's the molarity of the base solution? So what do we need to know to find the molarity of that solution? We need to know the number of moles because we have the volume. Right? So the volume is 0.01161 liters. Right? Just move the decimal place to the left. We need to find the moles. So if this is neutral, if this is stoichiometric, then the number of moles here equals the number of moles there because 1 hydroxyl, 1 hydrogen. And this is a balanced reaction. Okay, so how many moles do we have here? Well, we need the molar mass of that compound, right? 1.61 grams needs to be converted to moles. We can't go anywhere in this equation unless we have moles. So what's the molar mass of that compound? Well, let's see, we have 6 hydrogens, 6.06. We have 6 carbons, 6 times 12.01, and 1 oxygen, 16. So that's 88.06. There we go. We divide that into 1.61. And I get 1.828 times 10 to the minus 2 moles. So that goes up here. Why? Because if we know the moles of this, 1 to 1, we know the moles of that. 1.828 times 10 to the minus 2 moles. Divided by 0.01161 liters. So that's 1.5, 3 significant figures, 7 molar. Uh-oh. What did I do wrong? 1.828 minus, okay, 6. All right, so that's an error, right? If we did this right, 1.61, 8806. Let's be sure I did this one right. 6.06 for the hydrogen, 12.01 times 6, and then oxygen, 94.12. There's a mistake. Okay. So this is going to be different. 1.711. 0.01161. There we go. There's my mistake. Calculation error. That was 55. Let's see. Let me check the last ones I got marked off because we're running out of time. $62. Let's go down to 62. There it is. All right. 15 milliliters of 0.3 molar sodium phosphate react with 20 milliliters of 0.2 molar lead-2 nitrate. What's the concentration of phosphate ion left in solution after the reaction is complete? Okay, we need a balanced equation. So we've got sodium phosphate. This is 3 minus. This is 1 plus, so we need 3 of those. This is an aqueous solution. Okay. Now that's going to be combined with lead-2 nitrate. lead 2 plus, nitrate, 1 minus, this one needs to be 2. And that's an aqueous solution. So what does it yield? All right, you just double replace it, swap your ions. Nitrate with phosphate, nitrate with sodium and phosphate with lead. Sodium nitrate, you'll see from your chart, is completely soluble. Whereas lead 2 phosphate and this is 2 plus and this is 3 minus. This has to be a 3, this has to be a 2. Okay, this is a solid. Okay. You can set up your budget and balance using 10 units, but these are usually fairly easy to balance. 3 leads. Okay, 3 leads. That gives us 6 nitrates. And we need 6 sodiums now, which means 2 here. So 6 sodiums, 6 sodiums. 2 phosphate, 2 phosphate. 3 lead, 3 lead. 2 nitrate, 6 nitrate, and 6 nitrate. So it's balanced now. Now, what are we given? 15 milliliters of 0.3 molar phosphate. 15 milliliters of 0.3 molar, and then 20 milliliters of 0.2 molar. 0.2 molar. All right, now we've got everything from there on the board. What's the concentration of phosphate ions left in solution after the reaction is complete? So over here, the phosphates are in solution. Over here, the phosphates are as a solid. They're not in solution anymore. But maybe we've got some left over from this one, right? If this is excess, then we do have some phosphate left over. We have to determine which one is limiting. Right? So this one is 0.2 times 20 is 4 moles, right? A tenth of that would be 2, and 2 times a tenth would be, 2, that would be 4 moles of lead to nitrate. And this one is 4.50. That's not moles. Millimoles. Millimoles of sodium phosphate. Okay. So which one is limiting? Well, we can use millimoles. We just need to say, what's the ratio of this one to that one? Well, for every 3 of these, you get 1 of those. So if we take this and do we need to cancel lead to nitrate and leave us with lead to phosphate. So this is 1, this is 3. So 3 into 4 is 4/3 lead to phosphate. I'll resolve that fraction if we need to. This one, we need to get rid of sodium phosphate and leave us with lead 2 phosphate. Okay, the ratio here is 1 and 2. So 2 into 4.5 is what? Well, it's 2.25, correct? Millimoles of lead 2 phosphate. And this one is 3 into 4 is 1.33 millimoles. Okay, so this one produces the least amount. All of this is used up. Okay? All of this one is used up. So it's used up in terms of how much phosphate is over here. Right? If we use this one here, 1.33 millimoles of phosphate is over here. Excuse me, 2 times that. 2.66 millimoles of phosphate ions is used up. What did we start with? We started with 4.50 millimoles of this compound, which is equal to 4.50 millimoles of phosphate, right? Because it's 4.5 millimoles of this compound, and there's 1 for every unit. So this is what we started with. This is what we used up. And so that's 4, 6, and 14 is 8, 1. 1.8 millimoles divided by what volume? How many milliliters? 35. Right. So 1.84 divided by 35 milliliters is 0.053 or 27. 0.526 molar. Well, there's the closest one right there, 0.052. Right? That took a lot of work, but you got to practice these things. Otherwise, it's an acquired skill. You need a balanced equation, and you need to put what you know, and you find the limiting reactant. Right? This is the limiting reactant. So all of this one is used up, and it requires so many millimoles of phosphate ultimately. Where did it come from? It came from over here. So we started off with this many millimoles. We used up that much, and the calculation after that is simple. All right, that was, which one? This one, 62. All right, looks like I'm out of time. 64 is definition. When a solvent has dissolved all the solute it can at a particular temperature, it's said to be saturated. There it is, saturated. That's definition. And I'm looking for, well, there's one more I marked on here. Let me see if it's worth tackling. I should have left that one up on the board before, because it's based on the same reaction. What's the concentration of nitrate ion in the solution? Nitrate is a spectator. So all you have to do is find out how many moles of nitrate did you start with. You have the same number of moles at the end. You just divide by a new concentration because it's diluted when you add them together. So that one really is pretty simple. Okay, I think we're out of time. Yep, supposed to be done 2 minutes ago. All right, so next Tuesday, we'll have an exam. And of course, it'll be online, so you just need to be sure that you access the useful information document before you go into lockdown browser. Then you'll have access to that information during the exam. And remember, the exam will not automatically submit unless you tell it to. What it may do is when the clock runs out, it may ask you whether you want to continue. Then be sure and continue if you need to.